Hello and welcome to our second discussion around Module 2. I'm sorry, Module 1. Jumping right in, we'll talk again about setting up an analytics environment, and more particular talk about the things that you do inside of it to be sufficient for the first deliverable. So jumping straight in, our agenda. We're going to talk about packages, go over some of the things from a Module 1 perspective about Python packages, R packages, and then graphing from both Python and R. So packages and libraries. First of all, well, what are they and why do we use them? And the basic idea is it's a reusable set of items, collections of things that are useful, that are typically centered on a particular problem. They deal with a common functionality. For example, Pandas data frame is all around creating a structure for interacting with data in a essentially tabular fashion. Same thing with NumPy is around doing numeric calculations on things like vectors. And so they generally are focused on a certain problem. They're typically housed in some form of a repository, be it CRAN in the case of R, be it PyPy in the case of Python. Sometimes you call them packages, sometimes you call them libraries. The terminology is kind of varies by environment and language, but the basic idea is it is a collection of things that are meant to be reused. Sometimes they're platform specific, but generally speaking, especially in the case of Python and R, they typically are platform agnostic. There are versions of them, so they may have a particular version, and sometimes those versions may actually have breaking changes, so that from an example you see for one version of a piece of code might not work on all versions, so keep that in mind. And sometimes there are also dependencies, so one library might rely on another library which relies on yet another library, so keep that in mind. Generally, whenever you install them, the associated dependencies are installed for you automatically. There are sometimes exceptions to that, but generally that's the case. So talking about Python and Python packages. I thought I'd start off in general with kind of a demo here that talks about some algorithms that you're sometimes asked to do during a Python coding interview. There are some individuals, some organizations that feel that you should be able to write code during an interview. Personally, I'm not a fan. I think that it is a bit, depending upon your qualifications, a bit annoying to have to demonstrate your capability. But that being said, it is something that sometimes happens. It became very popular for a while. See it less so now, although sometimes there are the equivalent versions of it to where you maybe have take-on assignments to prove that you're competent in what you say you have done. So I took this from a link there at the top towards data science, 10 algorithms to solve for your coding, your Python coding interview. Some from there and a few from other places. So these might give you some idea of what you might do, or combinations of things you might do whenever you're asked to do something that's more complicated than converting from Fahrenheit to Celsius. So you might string together several of these sort of things, and if you do so, make sure you do give credit to where you found them. It's important so that we don't get into some negative things. So you may be asked to essentially reverse a string using either positive or negative integers, so basically reverse them. And the way to do that's to turn it into a string and then play the string back in backwards case, so basically reverse it. This whole thing centers on this colon stuff going on inside of the string. And that's basically the gist of it, is going from in this case, if it starts off with a negative, then you treat it a little differently by essentially kind of skipping over that first one, and then the same thing if you're just reversing a simple string or a simple integer that happens to be a string that you can convert it to a string. That's what that's about. Probably not all that useful in the real world, but could be something you see in an interview. So be prepared. Also then, and I'm trying to make sure if I need to blow that up a little bit because that might be a little small. So let's go a little bigger. Then moving on to the last thing there, the -1 is the magic, right? It basically says do that in reverse order. And so that's an example so that you can see it. And sometimes it's important to pick apart examples that you find just to make sure you understand what they're really doing. So this is an example of returning the average word length by dealing with the punctuation. Interestingly enough, this has a bit of a problem in the example that they gave. So if you take a look at it, the problem here is right here, right? It doesn't handle the ellipse appropriately. So basically what it's doing is replacing for the characters that are single characters, dots, and so on, getting rid of them, essentially stripping them out rather than replacing them. And you can see it calculates the random number, or the average number or length of the words in each one. But a little better solution, and it's not just because I wrote it, but because it actually works correctly, is to, rather than blanking them out in mass, instead replace it with a space, and then go through and replace all the double spaces with single spaces until there are no more double spaces. And doing that, then you get where it actually is spaced appropriately. And this is not to get too terribly technical, but it's called tokenization. So it's converting things into tokens. There are algorithms or libraries that make it a whole lot easier than this, but this is the basic idea, though. This actually might have some value, but if you're doing this, you're probably using some learning frameworks, scikit-learn and the like, to do the actual calculation rather than doing it yourself. But it is important sometimes to know the average length of the words in a string. Creating a valid palindrome by basically removing only one character. Again, kind of contrived. Probably you're not going to do this for real, but the idea is to explain that you can indeed do it, right? So in the case of the first one, and I'm going to go ahead and add a little bit to this so that we can see the results of each one, because otherwise what you're doing is just seeing the last one. So you can see here that this can be coerced into being a valid palindrome by essentially removing a character. And so to produce Ricard basically by removing the D. To do that, you've got several things where you're looking for, if the string is the same as the string in reverse order, then it's true. And you loop through basically removing a character from each location until it turns out to be true, and you can't do that with something like Mississippi. Arrays, pretty important to understand. Monotonic means either increasing or decreasing in a consistent fashion. So if it's either going up or it's going down, then it's considered monotonic. So in this case, 6544 is monotonic in that it is continually either staying the same or getting smaller. Same thing with 1, 1, 2, 3, 7. Those are monotonically increasing in that case. This is not, because there's some stuff in through here, right? So it goes down, then it goes up, then it goes down, down, and then back up. So that's not monotonic. Might be useful. There's probably other ways that you would do it. It's sort of, you could think of it almost as a form of time series analysis, but a little contrived. But again, these are the kind of things you see on a coding interview, because they may or may not be all that practical, but they are sometimes something you have to do to show that you can solve general problems, right? So this is basically around given two sentences, return an array that has the words that appear in one set, one sentence, and not in the other, right? So it's basically some set operations going on here. This you might actually do set operations. The example that they provided used the shorthand notation for the symmetric diff and the intersection. You can do the same thing spelling them out, right? So you can actually say set 1 dot symmetric difference of set 2, and then the same thing with set 1 dot intersection of set 2. And so those are the two different approaches. Set operations, important thing to demonstrate. You may or may not be doing them all that often. You're probably not going to be doing them in primitive sets. If you're using them, you'd probably be using some sort of data frame to do it. But it is interesting to understand. Prime numbers in an array, pretty useful. And so basically you're returning essentially a solution that is determining if a number is essentially prime that are greater than 1. So 2, 3, 5, 7, and so on. You can do the same sort of thing with a recursive solution, but the problem with a recursive solution, and recursion simply means that you define a function that in turn calls itself, right? Generally, it must have some form of a terminating condition. So these are essentially the terminating conditions, and this would be tail recursion because we're doing it after we check. So the basic idea here is that it will do the same thing basically. The challenge you have with this approach versus the iterative approach is the iterative approach will work for pretty much any size set, where recursion, there's a concept of a stack depth, and you can only recurse so many times before you run out of stack, essentially. So if you make n really big, it's probably going to blow up at some point. So those are things to consider. So, and with that, we can switch back over to the next thing. So talking about Python packages, and I'll go ahead and close this tab so we don't revisit it. Basically, the steps to do a Python package, I believe I outlined this last week. There's lots of different ways. You can install them in the case of Python using PyPy, and that's the typical repository you're going to use, although you can install any kind of package if it's properly formatted and you have a URL. Generally speaking, most things are in PyPy. Generally, you'll be using something like pip or conn to do the installation. Once you've installed the package, you still have to import it into your code so that it's available. You can alias it, and you can select certain elements out of a package, not the entire package if you choose to. So you'll see a common example is pandas is typically imported as PD, and then you'll do pd.something rather than pandas.something. An example in PyPy, if you wanted to read something like a Microsoft Access database file, if you go to PyPy and search for Access database, you can see Access parser there is available. And Access 1.1, the first one there, is not around Access databases. It seems to be around usability, perhaps. So you take a look at it, you figure out how do I get it, and then you typically want to take a look at the example of how to use it. This is a typical sort of pattern, especially if you're dealing with something that's a bit more unusual and interesting, and perhaps has a unique sort of usage pattern. So for example, if you're opening up Microsoft Word documents and extracting the text from them, you're probably using something like docx to do that, which is a library, and you'll want to pay attention to the example code of how to do it. Moving back to some additional demos, we'll talk about basic plotting with Matplotlib. This example is taken from data visualization with Python, which is available inside of the O'Reilly materials that you have access to. Pretty good. Most of the books in there will have example code that you can download. This first code is something I've written primarily so that I can use this in both a Linux subsystem versus my desktop PC's subsystem. So it'll work in both Linux and Windows using the Windows subsystem for Linux, so which is actually what we're running under right now. So if you take a look at that, you can see that we're actually running inside of Linux. And just to briefly show you that, there is a terminal running over here, and sorry for the weird slide. I'm running a early version of Windows 11, and it's got a few issues. This is the first time I've seen this one. So anyway, this is basically running on top of a Ubuntu 20.04 LTS instance. This is actually running inside of my Windows environment, a form of virtualization, but without the pain and hassle of creating a separate virtual machine. I'll talk about this more most likely later. One of the reasons you might do this is some of the packages do a little better if you're running inside of Linux than they do inside of Windows, so something to keep in mind. So some basic plotting here with Matplotlib. You'll notice also I'm running all of my examples inside of Jupyter, and you can see the kernel I'm running up here is Python 3. Even my R demos, I'll be doing that primarily so that it's a consistent experience, so that you're seeing the same stuff. Plus, it makes it for some nice display. The import is what I just told you about. We were giving it an alias, PLT. That's also fairly common, and we're importing pyplot and giving it that alias, not the entire matplotlib. And then that percent matplotlib inline probably isn't really necessary, but it tells it that tells Jupyter that it should show the graphs in line, kind of a default behavior anyway. So here's an example of basically creating some lines and doing the plotting of looks like x from 0 to 20, and we're plotting the square root against that. So somewhere in through here, 4 is going to be in through here, so 2 is right there, right? So we can see that it's basically working correctly. Very simple example, and we're whenever we do the plot, it gives back the actual plot and displays inside of Jupyter. The same sort of concept here of doing some figures, right? So making it a little prettier. Start throwing in setting the size of the figure to a certain size, so you can see it's a little bit bigger, and basically plotting the values as well, and then making it even nicer, actually setting some labels. One of the things you'll see in the rubrics is that setting labels and advanced settings is part of how you move up that rubric scale. And so here, adding a legend to it, so even more important, so you can actually see the square root versus the cube of a value series. That's basically, we're cubing one set and square rooting the other, so you can see that it almost looks like it's at 0, but that's just because of the scale is really big. Plotting a data set starts with reading it into pandas. So here's an example that I mentioned of PD, right? So we're importing pandas as PD, and then we're saying PD.read the CSV. In doing so, we've loaded that into a data frame, which is essentially like a table in memory. This leftmost column is the index. These are the attributes, or the columns that are associated with it. And you can see the results. And one of the nice things is you can actually do some plotting as well. So we're going to go ahead and, if we've got plot, pyplot pulled in, we're setting the labels, giving it a title, and then telling it to plot the data. Not a terribly useful graph because it kind of looks like squigglies, right? So probably not the best means of doing it. Tab separated values, this isn't necessarily about plotting, this is about reading, and you still use the read CSV method off of pandas, but instead you tell it the separator is a tab. You read it, we can take a look at the head, it should be the same basic thing, and then we plot it. This time we're doing a scatter plot, a bit more appropriate, because the other kind of just looks like a kid with a crayon or something, right? Here you can actually see that it is plotting the different values, basically comparing sepal versus petal width, so petal length, sepal length, so you can see the difference. The same sort of concept here of changing a little bit to the marker to be an X rather than just a dot. But again, it's about kind of making it look a little different, a little better. And then here's adding, separating it out so that we plot the various, what do you call it? Species, right? The petal versus, so this is the petal length versus the sepal width. So plotting those, I guess it's the measurements, is to do two different distinct values so that you can see that the differences based upon the dot or the cross that's being used to indicate. Also, it's not unusual to deal with the Titanic data set. We're basically loading it in, taking a look at it, then plotting some bar graphs, right? So nice way of seeing things like the gender versus age, and see that the males were, for whatever reason, a bit older, and the females were. Then also plotting age versus class, so ages in the various classes, and seeing that the second class had the youngest kind of average age. Then doing a histogram, seeing the breakdown of things by various buckets, in this case age, and how many are of what age, so you can actually see more of the shape of the data. And then looking at the fare of who paid how much, and how many people paid how much, I guess is the better way to say it. Then another histogram of age, right? And so the basic idea here is to show different ways of seeing it. This is pretty nice because it's exploding it out. It's got some labels on here. It's got the value, so where we can see the actual percentages of each one of the pie pieces. This is a really nice graph, so far above the basic pie chart that you might see otherwise. And then here, these are some useful, not necessarily graphing, but value counts is a nice thing because it shows you for a given attribute or variable or feature, what are the various counts of that. So it's basically doing a group by and then giving you the count of each one. And also taking a look at the values and turning them into a list, right? So quite useful. Again, a pie chart, the only thing that would be pretty nice on here is a label, right, or a title giving you a sense of what it's about. Stack plot, also quite useful and visually appealing. Lots of things. We've got our title across the top. You've got the legend over on the right side. Very useful, very well done. Nice use of color, and so on. And those are the things that we can probably kind of go ahead and wrap this up, right? Because that's pretty much enough of that. Moving back to the deck. Next, we'll talk about NumPy, and we've, as I mentioned, NumPy is basically a way of dealing with vectors and arrays and computations on them, including things like matrices. So to do this, we'll walk through each one of these. So one of the features that's inside of NumPy is, and you can see we're doing it as an alias as well, NumPy as NP, right? So we're importing it in, giving it NP as essentially the alias. That's again a very common thing you'll see in code examples, and probably you would consider that a best practice. We're also importing in PLT, Plotly, from Matplotlib, and then here we can basically set the name of a figure and give it a figure size. Pulling in NumPy as NP again with an array. Probably you don't need that second import. The first one would have been sufficient. Basically, that's creating an array and a list for the range of whatever that is, 1 million. So there's 1 million entries that are added to it, and then we can calculate the time it takes to square the array, and 2 different ways of doing the squaring. And you can see this first one is much faster. It only took 21 milliseconds versus almost half a second on the second one. So something to consider is that there are more optimal ways of doing, and this is using the native NumPy calculation versus this is using the native Python, essentially kind of a functional sort of approach of saying for X in my list, right? So something to keep in mind is there can be a much faster and a much slower way. May not become terribly relevant on the stuff you do in this course, but whenever you're doing this out in the real world, it definitely does, because the faster things are, the better often. So here we're basically creating a random 2-dimensional array. It's basically a 3x2. Then we're multiplying all of the elements in that array by 10, and then adding them to themselves. We're only seeing the second one of those, so if we were to do this, always a better way to do it. So there you can see this is actually being multiplied by 10. We're not assigning this to anything, so it goes away at the end of this evaluation. We're not setting something equal to that, so it essentially evaporates once it's done evaluating. Here you can see the basic type and the shape. Again, you're not seeing it because it is a 2x3, and the data type are floats, 64s. Then you can essentially create arrays from an array of data. So that's one of the things you'll see in the assignment is how do I convert from a Python array to a NumPy array, and you do so by using numpy.array. And it returns back an array. Similar sort of thing. This is basically doing a 2 rows and a 4 column matrix using the same basic approach. This is an array of arrays, right? And so the shape is going to have to line up correctly, so that we can see this as well. We'll go print the number of dimensions is 2, and what is the shape? It's a 2 by 4. Also, taking a look at the data types of the first array, it is array 1 is a NumPy array made up of, or it is a basically it's a NumPy array made up of floats, where the second one is of integers. So there's one of the characteristics. Taking a look at other ways to create things, you can create an array of all zeros, a matrix of all zeros, and then empty of 2 by 3 with basically something that's close to 0, but just slightly off, and that's because of floating point issues. You can arrange the items or create a range of items by using that, and it's basically saying from 0 to 14, so 15 items starting at 0. And then here, data types for arrays, and I'm going to pick this up a little bit because we are going on. So these are this one is pretty important, understanding that you can do array arithmetic, and that'll become important in subsequent courses, and I'll talk a little bit about that in here in a minute, perhaps maybe in a future session, where there's something called a Markov process that is basically matrices being raised to a power to be able to determine state transitions after so many units of time. And so you raise them to the number of units of time that you're interested in. That's where things like NumPy comes in very powerful, because it does have capabilities like multiplying an array by itself. You can also raise it to a power. So it's not here, but if you do this, it's the same basic thing because we're raising it to a power of 2, or you can cube it, right? And that's where we're getting right in here, right? So it's actually raising the power using matrices mathematics of multiplying it times itself 3 times, basically. You can also do division and square root, right? So that's what this is at a matrix level. So quite powerful stuff, and we're only touching the top of it here. The same sort of thing of creating a range, then you can slice the various elements of the range, assign a range of it to a certain value, and so on. Again, because these aren't being assigned, I'm just going to go ahead and do a print real quick here so you can see the values of each one, and then I'll run it. Otherwise you'll only see the very last thing, which is going to be an array. Relining it's not liking that. Is it? All right. Oops. Trying to save that to something new so we can print it out. Okay, there we go. And so we're picking 5 to 8, and we're setting them equal to 12. So that's what this is doing. And in fact, that's one that we don't actually have to capture because it's doing it automatically. So it is basically saying take these 3 elements inside of the array, 5 through 8, and then basically assign them the value of 12. So you can do that sort of assignment. You can do the same sort of thing. It's basically doing a slice but with an update, right? So you're taking a slice and assigning a value. You can pick a slice, you can pull out 5 through 8, You can set a slice equal to a certain value, which is a variation on this theme up here, right? But it's just with a single value versus a range or a slice. Or you can set lots of different values. I'll go ahead and skip through all this because there is a lot here. Again, if you want to learn more, you probably want to dig into the link that I provided for this resource. So again, at the very beginning, back in the deck, this NumPy Basics, a pretty good resource as well. So with that, we'll switch over and talk about R, and I'll go ahead and close this so we don't forget it. I'll go ahead and save my changes. So R packages. Whenever we talk about R packages, you're talking mostly about CRAN. You can install roughly 5,000 of them, of the packages, kind of out of the box if you're so inclined, or you can install each one of the packages as you need them. When you go to the cran.rproject.org, you'll find that it's not PyPy. PyPy is a more modern, more updated version with a lot more capabilities and elements in it. That's partly because Python has a much more active group currently. There was a time that was a different story, but in the past 2-3 years, Python has exploded and R is shrunk. So that's something to keep in mind. When you go to look for something, it does leverage Google search, and there's not quite as many packages. So if you want to search for something that deals with a Microsoft Access database, you can see it returns something that looks a lot like Google search result, because they're actually leveraging Google. And the closest you've got there is package MDBR, which works with Microsoft Access files. So that would be your best bet. So if you were to pick that one, it goes through the process of going and taking a look at the source code if you're so inclined. If you want to use it, then you go into, if you're using the RStudio, you'll go and click on the tools and say install packages. You'll say from CRAN, and you'll type in RDBR or MDBR and install it. If you're doing it a command line or inside of a notebook, such as I do, you'll be doing something called like packages.install or install.packages, and then parentheses quote in that name, MDBR, and so that's how you install it. Moving back over to some more demos, we'll talk about R programming interview questions. So questions: how do you find all the preloaded data sets in R? You do data, parentheses, and it shows you all of the data sets that are available to you inside of it. The most common ones that you'll see is things like Iris, and probably, surprised Titanic isn't in here, but it's one of the ones you use the most. Also MT cars, motor trend car road test, and that's one that's commonly used. So preparing you for that first R interview. So what's the next statement do in R? And the short answer is it's essentially skips, right? So it's similar as a continue in a while loop. In some programming languages, it basically says whenever this condition in front of this is true, if that happens, the next is evaluated, and it takes you back up and starts back over rather than hitting this line. So that's why if it's even numbers, we skip it, and you get only odd numbers. So how do I assign a variable in R? There's at least 3 ways, and that's one of the ones that somebody might miss. You can do the typical myvar less than equal to, so the arrow 1, and you can also say it's equal. This is assigns to is kind of the way that would be read, but you can also go the opposite direction. So you can say 3 is assigned to myvar. You don't see this much. It could be a little confusing to somebody reading it, but it is legal, so you could do so. How do you write a function? And that's the syntax. So function is assigned, and then keyword, or my function is assigned function. Then arg1, arg2, dot, dot, dot. It basically means it'll take a variable number of arguments. And then in this case, we're going to do nothing more complex than add things together. So we are passing in 1 and 2, and we're getting back 3. How do you do string concatenation and use the paste command? So be prepared with that sort of thing. And this is where an example of installing a package. In this case, we're installing Party, and what we're doing here is going to create a decision tree for Boston homicides data set that is available inside of the data, and going through talking about yeah, it doesn't like Party, so it's probably a problem. I need to take a look at that. I thought it worked earlier. Maybe I may have clicked something indirectly. Let's go take a look. Yeah. So something's up with that. It may be because I'm running. Let's do it this way. And I forgot to do this. Conda activate is a way of switching environments. I was in the base environment, so I'll do the same thing again. That's interesting. Maybe something to do with that environment. Anyway, moving along, back and through here, decision tree. Next question is, what's a while loop and a for loop, and give examples. So this is a simple while loop, and you start by assigning some condition that you're going to test inside of the while loop. So in this case, we're saying the variable is assigned, begin is assigned the value of 1. We then check at the beginning of is this true? If it is true, we enter the loop and execute. Once that this execution completes, it considers the value again and goes until this is no longer true. And so that's why you see this. And so we actually hit 6, which is going to be greater than 5, and that's why it prints out that way. For loop, similar concept, other than you give it a range. So in this case, we're saying for value is in the range of 2 to 6, and so it writes that out, and those are inclusive and similar sort of concept. So those are important things to be able to master. A little bit of an early, but I kind of figure the more I tell you, the better at this stage. You can always skip over it. Another example is this concept of Monte Carlo simulations. And Monte Carlo simulations are pretty simple things, really. It's basically you do some sampling, you do a loop that goes through those samples, doing some application of a function to it. And so lots of fancy math, but at the end of it all, that's all it really means. And in this case, a good example is estimating the value of pi, and it's doing so using some mathematical foundations. You're using Buffon's method of basically pin dropping, needle dropping. Comes down to, you have a formula that you're using to essentially serve as the model, and you generate a random uniform distribution. That's what the run if is a typical function. The R is going to be for normalized, basically. So It's a random normal distribution essentially. And you tell it that you want that many, the number of samples. Multiply it by 2 minus 1 gives you an x and y location. You're essentially testing to see if the pin drops within a circle area, so that you can calculate pi by using the function essentially pi hat is equal to 4h over n, and h is the number of hits, n is the total number. So and checking with the expression here, that's basically the way that you determine if it's in the loop or not. And that's what this is basically doing, is adding up all those ones that are in the circle, and then given that, you multiply it times 4 and divide it by the total number of times that you created it. And you can see it does a pretty good job approximating pi. It's a very old sort of solution, but it is quite useful and is a good example of doing some iteration, and pretty good example of something that's a bit more complex than Celsius to Fahrenheit conversion and vice versa. And I'm not going to go into a whole lot more on Monte Carlo simulations. You will see it again in future courses. It sounds more complicated than it is. It's basically a loop with some samples and some randomness, and determining if something is in a set and doing some aggregates across the resulting value. Switching back to our examples. So Python graphing. So moving on back over to the graphing side of things. The simple way is using, we've kind of talked a little bit about it, Plotly is similar to Matplotlib, that kind of concept, or ggplot. Those are all doing similar things, and this is basically just plotting some values. This is an example of something that's a bit fairly mature, and probably would be from a is it good enough perspective. Probably is. You've got a nice little legend over to the side. They're color coded. You got a title on the various things plus a title for the graph. Pretty good job. So going over and looking at a few of those. This is a similar sort of version, I'll go ahead and talk about this briefly, of the pin drop approximation of pi. A nice visual representation of seeing that whenever things are in the circle, they're color-coded blue. When they're out of the circle, they're gray. And they're determined to be in the circle by using this. So the set is squared plus squared is less than half squared, because we're in a 1 unit circle here. So a pretty nice visualization of the pin drop that we just saw in the previous example. So examples of some Python graphs, and I'll go ahead and just kind of go through a few of these. So a stacked graph, and we'll just run through them. And you can see a nice example here. Again, we got the Y label being set. The labels across the x-axis, pretty nice. The title is on the whole thing, and we've got a legend. So pretty good job, and a nice visualization. Plus, it's got some additional lines drawn in, so some subplots going on here. So pretty good stuff. Some categorical values being plotted again. And this one probably not as great of a job, because we don't, I guess we do have a legend. We don't really have a title. It is a way of showing activities across different states. And this is basically the way that you might plot categorical values. And also this is showing a series of plots in a single figure, so pretty cool, and something that you might want to make note of. And we've been going for quite a while, so I'll probably go ahead and skip on to R graphing. Similar sort of concept. We talked a little bit about it before. This is basically showing a very basic plot again, and then a bit more advanced. So we'll go ahead and go to the next. This is a pretty good example of what you would want to shoot for. Obviously, this is around the IRIS data set. The various species are over here on the right side. They're color-coded with what they are, and we're comparing sepal width with sepal length as a way. And the whole point of this particular type of graph is to show that it could be challenging to separate these different species based upon in this dimensional space, because the blue and the green are pretty well commingled, right? It's kind of hard to draw a line. You might be able to draw a line getting all the R over together, but blue and green, this isn't a good way to discriminate between them. So moving back over, plotting iris, and this is taken from public health, Columbia.edu sites, default files, and so on. Do feel free to take a look at it if you're so inclined. Installing a ggplot2, and then we'll take a quick look at the iris data set once that finishes. And then when we plot using the library, and this library is kind of equivalent or similar to the import in Python. Excuse me for 1 second. I thought I was going to sneeze. So anyway, and then similar, so you're basically creating a scatter plot here, and then doing things like setting some labels as well. So you can see pretty nice graph. That's the sort of thing you would shoot for. Here, a little similar, but we're changing up things a little bit. A different sort of indication on the this is doing a point versus this is just a circle, and then through here a scatter plot with a small dots more so than the others, and then here we're getting into a more advanced graph, right? So we're seeing it's a scatter plot with a nice little gradient over here telling us the scale color gradient showing us the density, so that the darker is bigger and lighter, so yellow to red, and red being bigger, and then the species using separate tags. Very nice graph. Box plot, pretty nice box plot. It's got the things that you would expect. Title, and the X and Y is named appropriately with subtitles on each of the different species. And the box plot is a very nice graph for showing the distribution of things. The more advanced version of the box plot, prettier, different colors, slight variation on the theme, showing kind of what is it, the mean in a nice way, as well as the distribution of the box plot. Histogram, so with sepal widths, a stacked bar with or a stacked histogram. It's broken down by species. That's a very nice graph. So these are the good examples of graphing, and this is taken from a book out of your O'Reilly, off of this website. So if you feel inclined to go and find something like this and use it, do feel free. Just make sure you give it credit, right? That's the only thing I ask of you. And with that, we've reached the end. Let me know what you think of this, if it was useful, if it helped you, if it confused you. I want to help you guys be successful. Stay safe. We'll talk again next week. Actually, we'll talk again this Thursday. All right. Have a good evening, and the rest of this week until Thursday.